Good afternoon. We are going to do notes on Trig point 18. In the book, it's 4.7, and it has to do with inverse trig functions, which is a big topic. So first thing we're going to start with is finding exact inverses. So this is part A. And so for example, inverse sine or arc sine of 1/2, what does it equal? So what you have to think of is sine of what angle equals 1/2? Well, we know that sine of pi over 6 or 30 degrees equals 1/2. So the arc sine of 1/2, you're looking for the angle. So the ratio is inside the arc and the angle is what it's equal to, which is reverse from what we're used to. Okay, example 2. We have arc cosine of 1. And we know that cosine of 0 is 1, so the answer is 0 radians. So arcs just work backwards when it comes to memorization. Now, the most complicated part, though, of inverses has to do with the restrictions. The restrictions on the domain of inverse functions. In order for our math to work on inverses, they have to actually be a function. So what I want you to do is I want you to do 1, 2, 3, 4, 5, 6 little pairs of axes. So kind of medium-sized, but you can do 3 and then 3. And then we're going to draw on them. 1, 2, 3, so 6 of them. That's how many we're going to need. Okay, so first of all, what does the graph of an inverse look like anyway? Okay, so we're going to start by just graphing sine of theta. And we're not going to do a scale. We're just going to graph it like we would normally. So, you know, sine always comes up through the middle. Comes up and then down and then up and then in the opposite direction. Down, up, and then down. So that is your sine function. So when you do an inverse, the function is reflected across the line y equals x, because that's what you do is you replace y and x. So we're going to draw a line that goes through the corners of the squares. And that is the line y equals x. So the inverse of sine reflects across that line, and it's kind of tricky to graph. But basically it overlaps, it forms an S here. So it comes with a curve, and then a curve, and then it follows the same pattern. Going that direction. And then following this pattern here, curve, curve going that direction. So this is your inverse, so arc sine of theta. And the problem with arc sine is that if we draw a vertical line through the function, it hits the function a whole bunch of times. So this means that if we take the entire graph, it means that our arc sine fails the function test, which means none of our function math will work if we use the entire curve. So what mathematicians said was, okay, what if we take arc sine of theta and we only keep part of it? Can we then calculate everything else from that part? So the section that they kept, if I can show you, if I can highlight it, it kept just this piece of it, which is kind of an S-shaped piece. Looks like that. And on the top edge, it's pi over 2. Right and left is 1 and -1. and the bottom edge is negative pi over 2. So in this, your x values are less than or equal to 1, greater than or equal to negative 1. And your theta values, which are your y values in this function, are less than or equal to pi over 2, greater than or equal to negative pi over 2. So that's the piece that they chose to keep, because if you do the vertical line test, you can tell it's a function and our math won't get messed up. So another way to show the domain of arcsine of theta is that it goes from pi over 2, which is straight up, down to negative pi over 2, and it includes all the values that fall in quadrants 1 and 4, and it excludes those two quadrants. So that's your domain of arcsine. If something falls outside of that, you can't calculate it. Okay, so that's sine. So we're going to do the same thing with cosine. So for cosine of theta, let's just draw the curve first. So it always comes down before traveling back up. And then it's symmetrical. So it comes down and down. So there's your cosine curve. And now we're going to plot the line y equals x, which goes through the corners of the squares through 0, 0. That's our line of reflection for an inverse. And if we reflect that across the line, this value is now over here. It curves up, over, and down again, like that. And then here, it curves that way. So it's reflected across that line. Again, it actually fails the vertical line test because you can, if you run an x value through, you get multiple y's. So out of this curve, they decided to keep this much of the curve. So that much of the curve is kind of S-shaped, and your x values are negative 1 to 1. Your y values are from 0 to pi. So for cosine, theta is less than equal to pi, greater than equal to 0. And again, your x values are between 1 and negative 1. All right, so another visual of this, so this is, sorry, I didn't label it. This is your arc cosine theta. So your domain of arc cosine theta, it goes from 0 to pi, so it starts at 0 in quadrant 1, and it goes all the way over to quadrant 2, which is, of course, pi. And there are no values in the other two quadrants. All right, so the third and last one we're going to draw out for inverses is tangent. All right, so tangent. Tangent graph crosses at 0, 0, and it's got asymptotes at negative pi over 2 and positive pi over 2. And the curve actually is an S shape. It comes up and over. So to find the inverse of tangent, we're going to use the line y equals x through the corners. And draw the new curve. And the new curve has asymptotes that are reflections. So the asymptotes are horizontal. pi over 2 and negative pi over 2. And the curve comes over and up and over again. So unlike the cosine and sine curve, this arc curve doesn't have a problem. It doesn't have a problem with domain because it passes the vertical line test. So let me quick sketch. We'll do our two other coordinate axes here. So the graph of arctangent of theta has an asymptote here at pi over 2, asymptote here at negative pi over 2, and then you have this curve that hits 0, 0. So on this curve, your theta values are less than pi over 2 because they never touch the asymptote, and greater than negative pi over 2. Okay, so in summary, the domain of arctangent goes from pi over 2 exclusive, so not including pi over 2, to negative pi over 2 exclusive, and it lands in quadrants 1 and 4 with nothing in the other two. So that is your picture of your domain of arctangent. All right, so part C, let's practice calculating inverses. Practice calculating inverses. Okay, example 1, we're going to calculate the arc cosine of negative radical 2 over 2. Okay, so right away, your reference angle from memory, your reference angle has to be pi over 4. And this is a negative value. So normally cosine is negative in areas 2 and 3. So if I graph my reference angle, I could have a pi over 4 reference angle here, or I could have a pi over 4 reference angle here, because in both of those spots, your cosine is negative. All right, but here's where you need to know the domain of arc cosine. So the domain of arc cosine, theta has to be less than equal to pi, greater than equal to 0. So the domain of the arc cosine is from here to here. So we can only pick values that land in the domain. That means this one is out of the running. So what we're left with is this angle here, and we need the actual angle, so 1 pi over 4, 2 pi over 4, 3 pi over 4. And that's what this is equal to, is 3 pi over 4. So you really didn't need to know the domains pretty well. Let's do another one of these. Example 2. We're going to do arctangent of square root 3. Okay, so first thing you need to do is come up with the memorized reference angle. The reference angle is pi over 3, or 60 degrees. All right, this is a positive radical 3. So because the sign is positive, we know that tangent is positive in quadrant 1, where sine and cosine are positive, and quadrant 3, where sine and cosine are both negative. Okay, so let's draw a pair of axes. And we have one angle in quadrant 1, so it could be that one. That's your pi over 3. Or it could be in quadrant 3, which is this one. Could be pi over 3, one of the two. So here's where we're going to do the domain. The arctangent domain is from negative pi over 2 to positive pi over 2 exclusive. So negative pi over 2 is here, exclusive, to positive pi over 2, which is here. So the only one of the triangles that falls in the domain is this one, so that one is out of the running. So this angle, the reference angle is pi over 3, and in this case, the actual angle is pi over 3. So your answer is pi over 3. That's what arctangent of radical 3 is. Okay, so that's how you calculate arc angles using their domains. So Roman numeral 2, we're going to go to composites or compositions. Okay, when you're dealing with compositions, you always do the inside first, and then you do the outside second, just like order of operations. You have to use the domain restrictions on the inverse, because your regular functions don't have domain restrictions, just the inverses do. So there's a few of these that are what we call always true. These are identities. Sine of arcsine of x is always going to be x. If the arc is on the inside and sine is on the outside, it's always x. Cosine of arc cosine of x is also x. Tangent of arctangent of x is also x. And this is true, but you have to be careful. This is only true for x values in the restricted domain, the domain of the inverse. So that's the limiting factor, is the domain of the inverse. All right, so let's do an example. Oh, and then, so these are always true. And, oh, these are the ones with the restrictions. So the restricted ones are if you've got arcsine of sine x equals x, arccosine of cosine of x equals x, arctangent of tangent equals x. So these ones are always true, and these ones are only true for the x values in the restricted domain. All right, let's use these for a practice problem. So here we go, example 1. We're going to find sine of arctangent of 1. Okay, so how do we pick this apart? Okay, first thing we do is we concentrate on the inside. Inside comes first. So on the inside, the reference angle is pi over 4 because tangent of pi over 4 is a 1. This is a positive 1, so the pi over 4 can only occur in the quadrants where tangent is positive, which is quadrants 1 and 3. 1 because sine and cosine are positive, so tangent is positive. 3 because cosine and sine are negative, so tangent is positive when you stack them up. All right, so that's the first thing you need to do. Where's my ruler? I'm going to draw these out. Let's draw a graph. Doesn't have to be a very big graph. So, excuse me. All right, so we have two possible pi over 4 angles. We've got one of them in quadrant 1, which is this one, pi over 4, and the other one in quadrant 3, which is this one, pi over 4. Okay, so we've restricted where it can be based on where tangent is positive. So we have 2 here. So then the second part of this is you're going to take the outside function And this was pi over 4, right? So you take the outside function, sine, and you replace the inside with what it equals, which is pi over 4. And we know that that is going to be radical 2 over 2. The question is it this pi over 4 or this pi over 4? So the restriction that we have for arctangent is it has to go from positive pi over 2 exclusive to negative pi over 2 exclusive. So that one's out of the running. So we're actually going to really truly use pi over 4 as our angle. And that means that it's a positive radical 2 over 2. All right, last one here. These are kind of weird little problems. They're not too bad once you do a couple of them, but they are a bit strange. What we're going to do is find an algebraic expression that is equivalent. Equivalent means same value looks different. Is equivalent to y equals cosine of arcsine of x. Okay, so here's the process. I'm going to put the directions on the right and then the actual numbers on the left. So number 1, use the inside to create a triangle. Okay, so we're going to use the fact that whatever arcsine is equal to some angle theta, which means theta equals arcsine of x. So our triangle, we'll just draw a right triangle here to keep it simple. There's your 90. There's your theta. And opposite over hypotenuse is what your sine is equal to. So it's x for the opposite over 1. That's how you get your x. Okay, that's the first step. Okay, second step. Use Pythagorean theorem to find the third side. Okay, so let's do that. This is a leg. We'll call it A. So a squared plus x squared equals 1 squared. That's your Pythagorean. And I need to find a value for a. So I'm going to subtract the x squared over. So a squared equals 1 minus x squared. Take a square root. A equals the square root of 1 minus x squared. And we're going to put that on the drawing. A equals the square root of 1 minus x squared. Okay, so then your third step is you're going to use the triangle to find the composite. So ultimately what we just did was we replaced arcsine with theta. So y equals cosine of theta. That was our replacement. Using our diagram, it's adjacent over hypotenuse. So that's going to be square root 1 minus x squared over 1. And then you just substitute the theta back out. So y equals cosine of arcsine of x, and that equals square root of 1 minus x squared. That would be your answer. So again, you use the inside to create a triangle. So you replace this with theta, so theta equals arcsine of x. So sine of theta is opposite over hypotenuse, so 1 over x. That gives you 2 sides. And it's whatever is in here. That's what's going to give you your opposite over hypotenuse. Use Pythagorean theorem to find the third side. Then use this triangle now to find the composite. So then you go to the outside. Cosine of theta is adjacent over hypotenuse. So 1 minus x squared over 1. And that is your equivalent expression. You're looking for an equivalent expression. You might want to save these directions and keep them handy for when you go do these problems. Again, it takes a couple times through them to get the swing of them, but then they're pretty monotonous after that. Okay, that is the end of the notes. Have a good afternoon.